speaker will be Claude Roux. For those of you who weren't in the earlier session, we had to switch Claude with Skip because we had Claude scheduled at the same time in two different rooms. So anyway, he'll be speaking about glitter, the ideal trace evidence.
Thank you, Amy, and good afternoon, everyone. Yeah, I couldn't really split myself in two halves, unfortunately, so I have to rearrange the program. So this project, I should probably immediately acknowledge my co-authors, especially Richard Cam. Richard did this project as part of his honours project at the University of Technology in Sydney. So it was a very small project, so there is no big pretension, but I thought there was a few interesting things to share with you. Perhaps let's, to start, go back to something I mentioned yesterday in passing, and really this point that traces are really central to anything we do in forensic science. And I'm sure I'm just preaching to the convert here, but traces contain the fundamental information about the crime itself and about the people involved in the crime. So without going into the details, we all know that we can not only identify, which one is it? Laser, yeah. We all know that we can not only identify the people involved, but sometimes even more importantly, reconstruct the event. And obviously some trace types are more amenable to give some information about the reconstruction of the events or the activity that happened, and others are much better to get towards the line of a source attribution. Now, glitter can be very interesting evidence type here because potentially it's highly polymorphic. And in addition to that, it has a lot of characteristics that could sometimes bring a lot of information about the actual activity that happened. So first, as a way of introduction, a few important points that if you don't know what glitter is, I've got two girls at home, including a teenage girl, so I probably wouldn't be the right person to do some kind of a population study or prevalence of glitter in the background population. But it's all man-made pieces of aluminum foil, but more often little tiny pieces of plastics. It's cut in various different shapes. It has different colors. It can be different optical characteristics. It's been around for a long time. But recently there has been a bit of a resurgence or a bit more interest, to consider that as trace evidence in criminal cases. And I know Glenn Schubert has a few interesting cases. Bob Blackledge in the past has presented a lot of information about glitter. Now, what could be the ideal trace evidence? So, especially when you talk about glitter, it's nearly invisible. So it's so small that it's hard to see under normal conditions. So it may be a problem for the analyst, but if you put in the shoes of the criminal, it's probably a very good thing because it's the typical type of trace evidence that is transferred unwillingly, and it's what we like. It has a high probability of transfer and persistence because it's so small. I would say it's one of the typical trace evidence that is transferred according to the Locard's exchange principle. It's highly specific, highly selective. I mentioned that before because it exists in a lot of different shapes, different sizes, different thicknesses, different colors, and so on. Then, if it's found, no, if it's detected, it's not that difficult to be collected. It can be tape lifted, or it can be simply hand-picked depending on the amount of glitter you have. And it's relatively easily characterized using simple optical means, and I'll go back to that. And then it's relatively easy to build a database. Now, I should add at this point, it's not the point, to build a database quite often is not difficult in almost any field. It's more the question to maintain the database up to date, which is an issue. So here, obviously, we would need to keep in touch with the industry. So the aims of this project were pretty much a big databasing exercise, if you want, and characterize and differentiate different glitter products, including products that we purchased in Australia, so available in the Australian market. Then determine, try the common techniques, see how it would work, their relative value, limitations, and so on, and try to see whether we can identify any trend in terms of brand, country, color, etc. And build a database. And then in the end, I'll get back to that, but we've done a blind test. So the samples we had a total of 239 glitter samples. So we had almost half of that were provided by Bob Blackledge, and the rest was purchased in Australia. So we've got the list here of the different types of glitter, where they've been purchased. And if you can't read it, I'm sure you can download the presentation later. In terms of the analytical scheme, so we did an optical examination, the low power stereo microscope, did some microspectrophotometry. We did some comparison microscopy and surface texture. We looked at the FTIR. We construct a database using FileMaker Pro, and we did some blind tests at the end of the process. So a few general comments here. First, we found that no glitter samples were found to be manufactured in Australia, which was not necessarily surprising. And most of them were manufactured in the United States and China in particular, and it's not surprising. All the results were tabulated and based on the shape, the color, size, and area, and assorted into common classes. So a few information here. So here immediately we saw that when we talk about the most common colors. So interestingly, we found blue was a very, very common color, and I'm just thinking now when we look at fiber population, blue comes up very quickly as well. But then interestingly, again, something we see with fiber population studies, very quickly you go down. So just by simple subjective examination of color, you can see that you have already some kind of distribution which is interesting. But we all know that in our field we have limitations when we look at color with the naked eye, and we've got all the issues of lighting conditions, the angle of observations, etc. And this can be even more difficult with glitter because they are quite often highly reflective surfaces. So it creates some extra difficulties, if you want. So we went further using a microspectrophotometry. Before that, when we look at the shapes of the glitter particles, what we found in some cases, so we looked some very simple shape denominations, such as hexagon, square, and hexagon, or pentagon, etc. So the thing to show you here, obviously this is not a real hexagon, this is not a real square, this is not a real hexagon. What I'm showing you here is in a packet of glitter, sometimes you had some inhomogeneity. So it means you had a lot of glitter particles that would be hexagon, and then you would have a particle like that which would be a bit chipped or wouldn't have really the right shape. So it's something to be aware of in cases or when we do some kind of classification. But when we in the end classified by shape, we found that hexagon was by far the most common type of shape, and then we had square, and then very quickly it goes down. The fact that hexagon is a common shape really confirms previous studies that have been done in the last few years, which also found that hexagon was pretty common. Now, we can think then if you have, again, a less common type of shape, such as, even sometimes you have a heart shape or things like that, it has obviously potentially more evidential value. As part of the project, all the images were captured digitally, and the student used some kind of a software system to do some measurements. So to measure some parts of the glitter, so take some dimensions and take some surface areas for the various types of samples we had. In terms of the microspectrophotometry, a first issue we had, and you'll see the spectra, is glitter is so reflective. So quite often, we have the axis is in negative mode because simply, it's more reflective when you examine the glitter compared to the white standard we use. Overall, we found it provided little discrimination on the top of what we would do, in terms of optical determination of color. And here you've got a few examples with a few different samples, and sometimes you have different spectra for the same sample. So again, there is an inhomogeneity problem. Another thing to be aware of as well. So for example, here you've got two spectra which are, relatively similar, but they come from, again, from different samples this time. While here you've got, again, some different types of discrimination for different samples. In terms of the FTIR, so we did an analysis with an ATR objective, so it's a surface analysis just at the surface, and we did both sides of the glitter particle, and here you've got some kind of distribution we obtained. So, and you can see, you can see that essentially there is a lot of PET for glitter. And in some cases, if I go to the next one, the things that is very useful to know is that we found that PET is mainly found in American products, and other countries use other types of polymers. So again, could be an interesting indication or piece of information in terms of, in the case of investigation. This is an example of FTIR, where basically we had two different types of polymers between the top and or the outer surface or the inner surface. So again, it can be very interesting to remind people to do the analysis, for both sides of the glitter particles. Now, things we thought about that could be very interesting to do, it would be to expand this sort of analysis, but in the Raman, with Raman spectroscopy, because obviously it's a technique that would be ideal to analyze glitter. Another thing that we think we should expand is obviously, perhaps some elemental analysis of some kind. And I had the information from Bob Blackledge that there is a paper submitted about a technique which basically works on the density. So try to analyze the density of small particles, such as glitter, amongst other things, using a technique called magnetic levitation. And in these experiments, they found that from 11 glitter samples, they could classify that in 3 categories. So again, you can see that there is a huge polymorphism for this type of material. Now, the main aim of the project really was to build this database and see how it would work in terms of identification system. So this is just screen of the database. So you can see you've got the brand, the shape, the size range. So there is some kind of number, the color. Then you've got the size average, and then you've got the area range and area average. And there is each time a microspectrum and FTIR spectra for both size of the glitter particle. And here, for example, you can see that you've got one side of the particle is an ABS plastic, and the other side polyvinyl chloride. Now, this is a sort of acid test of the work that the student did. So he was given 15 samples, blind test, so he had absolutely no idea where these samples came from. They were given to him with the task of do the analysis with the sort of techniques he's been using, plus trying to test the database. And out of the 15 tests, all of them were correct. So there were absolutely no problem. So it's an interesting result. So I don't claim here that we would be able to identify any glitter, because obviously it was just limited to the samples that we had access to and we had tabulated in the database. But it's a good start. So this is a sort of sequence that was recommended at the end of this work, after all the work that had been done, with obviously some potential for more techniques to be added. So in conclusion, a variety of brands of glitter were characterized by optical, physical, and chemical techniques. Microspec was used to give an objective measurement for better comparative results. FTIR was used as well on both sides of the glitter particle to characterize the chemical composition, at least the organic matrix of the glitter. And the blind tests were identified correctly with the help of the database. So we have some further recommendation to look at various things, including possibly, things such as specific gravity section, Raman spectroscopy, some kind of elemental analysis. We saw density now with the recent work that I mentioned. And maybe take that to the next step then, because I mentioned the sort of trace characteristics of glitter. I only mentioned in this work, we only worked on this polymorphism side of it. But then what happens with transfer, persistence, as I mentioned, prevalence? All these things are important when we have to interpret this sort of trace evidence. And it's probably a big field for research if people are interested, and I'm sure we will try to continue some of these experiments, whether transfer, persistence, and prevalence. So just an acknowledgement to Bob Blackledge, who provided some guidance during the project, and especially provided half of the samples. So probably without him, there wouldn't be any project. And of course to you for listening. And again, I'll take this opportunity to thank NIJ, FBI, and the steering committee for inviting me to this wonderful symposium. It's always very helpful and great to share our experience with people like you. A few references that I'm sure, if you're interested, you can get that from the presentation, which will be on the website. And next year, if you don't know what to do in September, we host the Australian-New Zealand Forensic Science Society Symposium in Hobart, which is in Tasmania. It's a small island south of Australia, so it's still part of Australia. But it's a very lovely area, green, and we would, love you to come. I know a few people in the room here that came last year to Sydney, so I hope they spread a good word, and some of you will come back. So thank you.